So dear students, welcome to the new lecture of Basic Electrical Engineering. In this particular lecture, we will discuss about the losses in transformer. So this lecture exclusively is dedicated to the various types of losses in the transformer. Now let us start with. So a transformer when is operating and whether it is in on no load condition or it is on load condition, means whether it is unloaded or loaded with some impedance, right? So it possesses certain losses, and these losses are, the first one is the iron losses, and these losses are also known as the core losses, right? And these losses are associated with the core, the ferromagnetic material, basically the core of the transformer, right? The second type of loss is the copper losses, and in copper loss, because basically these losses are associated with the windings, so these losses are also known as the winding losses, right? The third type of losses are the stray losses, right? Now, these losses are quite negligible, very low in magnitude. So generally they are neglected while doing the analysis of the transformer, while determining the efficiency of the transformer, right? Then we have the dielectric loss, and dielectric loss is basically associated with the insulation of the transformer, a liquid insulation, a solid insulation, the oil of the transformer, like that, right? So the first one is the iron or core losses, and these are of two types basically. The first is the hysteresis loss, and the second is the eddy current loss, right? Now these losses are associated with the iron core, and that is why these losses are known as core losses. And the core, the ferromagnet, the core of the transformer, whether it is shell type or core type or whatever, right? That ferromagnetic material with which that core is formed is made up of iron or alloys of iron, basically. So we call it as either iron loss or core loss, right? Okay. So now these losses are because of the bidirectional nature or bidirectional flux. As we all know that in a transformer, the flux that is produced at the primary side of the transformer or in the primary winding of the transformer is of sinusoidal nature. It is given by phi is equal to phi m sine omega t. So this is the equation for the sinusoidal flux. So this indicates that the flux is a bidirectional flux, right? Like this. So this is the instantaneous value, and this is the omega t axis, right? So this flux leads to the hysteresis and the eddy currents in the iron core of the transformer. Now, what is hysteresis? Basically, let us understand what are hysteresis and what is the hysteresis loss, right? In our one of lecture, we have already uh, understood by the uh, magnetization of the ferromagnetic material. So we studied the BH curve. Now, if we talk about the BH curve once again, so in BH curve, we uh, found that when we magnetize a ferromagnetic material using the current, right? So let us assume that there is a ferromagnetic material or iron piece, for example. So this iron piece is wound with certain number of turns of a wire, right? and let us say a battery, a source is connected at this end, and some current I is flowing here, and this is, let us say, EMF, and the direction of current is this, right? Now the flux will start flowing from this end and will enter into this end, right? This is how the flux will be flowing, and so on. Okay, so right, like this. Now this particular ferromagnetic material, okay, it starts getting magnetized. Okay, now it, when it magnetizes, okay, when it is magnetized because of this current, right? How? Because if there are n number of turns, so the mmf here would be Ni, and H, the magnetizing force, is Ni by L, right? So this ferromagnetic material is magnetized. Now, if you want to demagnetize this ferromagnetic material, so what will you do? You will put I is equal to 0. Okay. So this iron will demagnetize. Now, generally, what is believed, what is desired, that when the current is 0, if I is 0, then H is 0. So if H is 0, so that means B should be or must be 0, right? So B must be 0. This is the belief, this is what we desire that it should happen. When you have magnetized a ferromagnetic material, once it is saturated, once it reaches to saturation, so when you want to demagnetize the same material, it should demagnetize properly with B is equal to 0 at H is equal to 0. Practically, this does not happen. Practically, what happens when you reduce the current? Okay, when I is reduced, okay, so the flux or the BH curve will not follow its original path, it will return by this path, and it will land to some point on B axis, means the flux density, y axis, when H is equal to 0. So at this particular point, H is 0, but B is not equal to 0. So that means our ferromagnetic material, which we were magnetizing, is still magnetized. That means it still carries certain flux. That flux is known as residual flux, right? It is known as residual flux, right? Now, if you want to demagnetize this ferromagnetic material completely, what you have to do, what you will do is, you will reverse the direction of current. Okay, so the direction of current is reversed. How will we reverse the direction of current? We will change the direction of battery, right? Let us consider the same ferromagnetic material. Now this time we have reversed the direction of battery. The current will flow like this. So now the current is reversed, right? So now this is if and this is I. Now in this situation, or in the above case, I is reversed, right? So that the residual flux become equal to 0. Now, what will happen? This ferromagnetic material, which was earlier magnetized in certain direction, earlier, let us say the direction of flux density was this. Now in this case, the flux density will be directed in opposite direction. Whether it is positive direction or negative direction, that is a different thing. Positive and negative is always in reference to something. If we have taken this as positive, then obviously this would be negative, right? But there is no thumb rule that this is positive or this is negative, right? Okay, so now what will happen? The ferromagnetic material will start demagnetizing, and at this particular point, B is equal to 0. But now we have another problem, or we have some another effect that we see in ferromagnetic material, and that is at this point H is not equal to 0, rather it is negative, right? So now, what is the ideal assumption? Ideally, when I is 0, H is 0, B must be 0, right? So this is an ideal assumption, but practically this does not happen. Now, at this point, your H is negative, B is 0. We call this as the coercive force, means the force which is applied to the ferromagnetic material so that the given ferromagnetic material gets completely demagnetized, right? Now, suppose that you keep on increasing the current in the same direction, that is the negative direction in this case. Okay, so if we keep on increasing the current in same direction, right? Then what will happen? Your ferromagnetic material will start getting magnetized in the direction opposite to the direction, this one, which it was in the first quadrant, right? So if we consider this to be positive, then this would be the negative direction, right? This is the negative direction. Now, at some point of time, at some value of H, your uh, ferromagnetic material now will be completely magnetized in the opposite direction, right? So now the saturation will arrive in this direction. Now, once the saturation has come, so what will happen? Now, if again you want to demagnetize the same ferromagnetic material, what you have to do? You need to reduce the current now. Okay. So when you will reduce the current, so it will start getting demagnetized, and let us say at some value of current where H is 0, or let us say at the value of current is equal to 0, H will become 0. And when H is 0, you will see the B. Here H is 0, but B is not equal to 0. So this is also the residual flux in the material. So that means whether it is the positive direction or it is a negative direction, or you can say whether it is the one direction or the other direction of current, the flux density is not 0 when I is 0, when H is 0. And we call this flux as the residual flux, right? Now again, what you will do if you want to demagnetize this, okay? So this is how it is going. So if you want to demagnetize this ferromagnetic material completely, so what you will do, you will reverse the direction of current once again. So the same ferromagnetic material we will consider, and we have reversed the direction of current. Now this is I, right? So what will happen? At this point, you can see B is 0, but H is not equal to 0. Rather, it is positive. So this is also the coercivity or coercive force. So this is something positive, this is the negative, right? Now, this will keep on going. This will keep on going if you keep on doing the same thing again and again. So what will happen if you see, okay, so what will happen? You will have the hysteresis loop. Now this is magnetized, it will demagnetize, land here, you will reduce it by applying negative force here, the negative direction magnetization, then reduction, then like this, and this is how it will keep on going, right? Now these are the hysteresis loops, which are because of the bidirectional nature of the flux. Now, in this example, we have taken the DC source, DC current, and we have understood it by reversing the direction of the battery and hence by reversing the direction of current. However, in case of the alternating signal or alternating current, we don't have to reverse the direction. It will be naturally reversed, right? So let us say, let us divide it in these parts. So this is the quadrant, this is first, this is second, this is third, and this is fourth, right? So 0, this is pi by 2, this is pi, this is 3 pi by 2, this point, and this point is 2 pi. One cycle is of 2 pi, right? 2 pi radians, sorry. So now, let us say this is some point O, this is A, this is B, this is C, this is D, for example. Now, here it is magnetizing. If you connect, now let us take an example of the iron core. Now you have connected it. You have connected an AC source here, and this is the secondary. Okay, so some current I, and let us say the voltage here is V, and induced EMF here is E1, this is V1, and here the induced EMF is E2, right? And the flux is flowing, for example, in this particular direction. Now, when you have applied the alternating signal to the primary of the transformer, it will result in the bidirectional flux. For example, from this point to this point, the core of the transformer, which is made up of the iron or iron alloys, so here it will magnetize, right? Now you can see the current is increasing, right? And then the current is naturally decreasing. Now what shall happen? The ferromagnetic core of the transformer should demagnetize, it should demagnetize. Okay, so here uh, you know from O to A, transformer core is magnetized. A to B core is demagnetized. Why? Because I is reducing here naturally. We are not reversing the direction of any current, or we are not reducing it manually. It is reducing naturally, right? The amplitude is reducing naturally. Now, for example, now it shall demagnetize here. Now at point B, at B, I is 0. Hence, uh, the core of the transformer must be demagnetized completely, right? This is what shall happen. However, because of the hysteresis, as explained earlier in this lecture, the iron core will not demagnetize completely, right? Okay, so but this does not happen practically. So that means this core of the transformer still have certain residual flux in it. Means when this point is reached at this point, when means at B where I is 0, uh, for example, for this, the direction of magnetic flux density is this one, and for this, the direction of magnetic flux density is this one, right? So at this point, right, at this point, B must be 0. This is ideal case, right? Now, this does not happen practically. Now, when this does not happen, that means when even if the direction of current reverses, the flux remains as it is in the same direction for certain duration of the negative half cycle of the transformer input supply. Means for this negative half cycle, for certain part, the direction of flux remains as it is, same. So that means some part of the negative half cycle is used or utilized to bring that residual flux of the core to 0 and magnetize the same core in the opposite direction now. Now, because this is a cyclic signal, this is a periodic signal, so this thing will happen again and again in every cycle of the input supply, and hence we have the hysteresis loop normally in AC magnetic circuits, for example transformer. So it is evident, it is obvious, inevitable to have the hysteresis loops and hence hysteresis losses in the transformers or AC magnetic circuits. We cannot avoid this thing because it is because of the bidirectional nature of the uh, you know uh, input supply. Now, how can we reduce this thing? Now, this is the question. We cannot, it cannot be zero. This hysteresis losses cannot be zero. Now, before that, we must understand how these are losses. These are losses because now this part of the negative half cycle, which could have been used for some useful work, is now being used to demagnetize the core first, then from here onward it will start magnetizing the core. Now it has only this much part of the negative half cycle for which the core will be magnetized to the maximum value, right? So that means we have wasted a part of negative half cycle, or let us say a part of input supply, in demagnetizing the core, which we could have used for some purposeful work. Now here the transformer will tend to draw more current, okay, so that it can demagnetize the core and magnetize it again in the opposite direction. So this loss appears in form of heat in the core of the transformer, right? So we cannot make these losses zero, but yes, we can reduce these losses by using some soft magnetic materials which have low hysteresis. For example, the silicon steel is better alternative for iron core, right? Similarly, we can use steel alloys, we can use some other magnetic materials which have low hysteresis, right? So this is how we can reduce the hysteresis losses. We cannot keep these losses zero. This is one thing. So now let us see what are eddy current loss. And the second category of iron losses is the eddy current loss. Eddy current loss is because of the circular currents which are formed within the ferromagnetic material, right, which is under the effect of bidirectional flux. So because of this bidirectional flux, or because of the time varying flux, what happens, we get some circular currents induced in the uh, ferromagnetic material, right? And these circular currents, because these are current, and these currents cannot be used for some useful work, so these currents means they appear in form of heat in the transformer. Okay, so when the transformer's core gets heated up, it is because of the iron losses, right? Yes, of course, the other losses are also included in that, but majorly it is because of the hysteresis and eddy currents which are formed in the ferromagnetic material because of the bidirectional nature of the flux. Now let us see. As you can see in this particular diagram, we have two types of, material, two types of formations of the ferromagnetic material. And this particular, let us say this particular material has, good thickness, right? So in this we have large circular currents, which we call as eddy currents induced. Okay, so now these you can see here, but when we divide the same iron piece in a number of thin laminated sheets, and then we stack them like it happens in the transformer. Okay, a transformer is generally, or the core of the transformer is generally made up of thin laminated sheets. Okay, so this could be in core formation, or this could be a shell formation. That is a different thing. Whatever type of transformer core we have, whether shell type or core type, uh, the core is made up of thin laminated sheets. The reason is that when we reduce the surface area, when we reduce the volume of the ferromagnetic material, and when we use insulation, proper insulation, so what we can do is we can limit these circular currents to a specific area, specific volume only. So they would not pass to another region, right? And hence we can reduce their effect, we can reduce their intensity in the core of the magnetic circuits such as transformer. Okay, so these are the circular currents actually. Now as iron losses are the sum of two types of losses, the hysteresis losses and the eddy current losses. So mathematically their formula is given here. For hysteresis losses, we have this KHFBM raised to the power x, and for eddy current losses, we have this particular formula KEF square BM square, where F is actually the frequency of the flux, and Bm is the peak value of the flux density, or you can say it is the maximum uh, flux density, right? So where kh and ke are the constants, right? Kh is the hysteresis constant, ke is the eddy current constant basically. These constants depend upon the um, material which is used to uh, manufacture the core of the magnetic circuit. It is also based, the value of kh and ke depends upon the quality of the material, upon the dimensions of the material, or you can say volume of the material, right? So these are certain, things on which the value of kh and ke depends, right? And then rest we have this equation which you can uh, study, right? After that, we have the copper losses. Now, copper losses are something which are associated with the windings of the transformer, right? So, when we have a transformer which is loaded, right? Okay, which is loaded with some impedance at the secondary side. Now let us consider in this way. So this is an AC voltage V1, and this is some primary current I1 flowing here, and then we have the secondary which is having some impedance or load impedance connected, right? So let us connect it here. So this is a variable load, right? ZL. Okay, so this is I2, terminal voltage V2, and induced EMF E2 here, induced EMF E1 at the primary side, and the flux is flowing, let us say, in this particular direction. Now when it is loaded, so this is the current in the secondary is flowing at its rated value. Ideally, it would flow at its rated value. Now, this in turn will increase the current in the primary winding. Earlier, when the transformer was on no load, so in that case, I2 was 0, but I1 was very negligible, which is only 2 to 5% of the rated primary current, and we call it as no load primary current, right? So this current is negligible. Because this current is negligible, so we generally do not consider the winding losses, right? But in this case, when the transformer is loaded, so in this case, because the current in both the windings is assumed to be flowing at the rated value, so now we cannot ignore the uh, losses in the windings of the transformer because of the resistance of the primary winding and reactance of the primary winding. So this is, let us say, R1, this is X1. So collectively, this is Z1, which is equal to R1 plus JX1, right? And similarly, in the secondary also, we have a resistance and a reactance. So this is R2 and X2. So collectively, it is Z2, which is R2 plus uh, JX2, right? So because of these resistance of the primary and secondary winding, we have the losses in the two windings of the transformer, and these losses are nothing but the I square R effect. Okay, these losses are nothing but the I square R effect. Now this I square R effect is nothing but the heat effect. So our windings of the transformer gets heated up. Okay, so now because these windings are made up of copper material, so we generally call these losses as the copper losses or the winding losses, right? This is one and same thing. Either it is copper loss or winding loss, it is one and same thing. So for both, the total copper loss in the transformer is the sum of the I square R in the each winding, right? Primary as well as secondary winding. Okay, now these losses, because depend upon the load variation, it is because of the load, and load generally is assumed to be varying. Load does not remain constant all the time, so it varies accordingly. It depends upon, like, if there is a transformer at somewhere at your colony, okay, so the transformer is distributing some voltage electricity to your houses. So if, let us say, half of the houses are, off, the load is off there, half the houses have the load on, so, and all of a sudden some more houses turn their load on, so, or off. So in this way you can say that the load across the secondary of the transformer keeps on varying, okay, naturally. Okay, so and hence we can say that these copper losses or these winding losses keeps on varying with the load fluctuation. Okay, so these are also known as variable losses. Okay, so copper losses vary as the square of the load current because of I square R effect, right? So now let us come to the next stray loss. Stray loss is basically due to the leakage flux, right? It is because of the leakage flux or leakage magnetic field. Now these losses are because very low in magnitude in percentage. So generally they are not considered when compared with the iron and copper losses. The next type of loss that we have is the dielectric loss, and dielectric loss is the loss that occurs in the insulating material of the transformer. That is, it occurs either in oil of the transformer or in solid insulation of the transformer. Okay, so oil is basically used to cool down. We have various types of transformer based on their cooling mechanism. So, and also it is used to provide insulation. So when the this oil gets deteriorated, okay, or the solid insulation gets damaged, so at that point of time the efficiency of the transformer gets affected, right? So over the time or over the usage of the transformer for long use of, when it is used for long time, so the insulation definitely gets uh, damaged or weakened. So the oil of the transformer is changed timely, and hence the insulation, the solid insulation is also done properly so that it can be long lasting, right? So this was about the losses of the transformer. Now one thing which is left is that uh, the iron losses basically are known as the permanent losses. Now why they are permanent losses? Because whether your transformer is on load or it is no loaded, okay, the primary current will be there. It would be rated current or no load current, that is a different thing. But in primary circuit, the current will keep on flowing. It is only the secondary which could be open or closed, but primary will remain closed. So the current keeps on flowing, and the current keeps on flowing. The losses in the primary, in the core of the transformer, sorry, will be there. So these iron losses are known as permanent losses. And as mentioned earlier, copper losses are variable losses, right? So this was all about today's lecture, guys. Thank you so much.